Okay, welcome everybody. Sorry for the delay there. Okay, a few administrative items to begin with. Oops, let's see if that, let's get that to go. Okay, so we've got over 300 students in teams now, which is great. Remember, by the end of this week, you should definitely be in a team, because as of next week, you're going to be working in a team in the lab. If you're not in a team, Dr. Tolman all week has been hosting meetings at the start of your tutorial time to group unpaired students. So there are two more tutorial times, one I think at 7 o'clock tonight and one on Friday at 3 p.m. I think. So make sure you join your appropriate meeting. And if you missed your tutorial meeting, go to one of these remaining ones, because we really need to get you in a team before next week. Okay.
Professor?
Yeah, go ahead.
Before you move on, I had a quick question. Okay, so me and my friend, we have registered as a team, but we are only a team of two. So will we be assigned like someone else, or can it just be the two of us?
You can do the course as two. It does make more work, but we'll kind of take that into account when grading you. So you can do that. Dr. Tolman, send him an email after this, or type it in the chat, and he'll keep an eye open for any unattached people in your tutorial section as well. Well, tutorial and lab section, and try to pair you up with someone. If we're unable to, you can do the course as a team of two, and we'll take it into account.
Yeah, that would be great.
So
if you could
just to confirm. Yeah, go ahead, Professor.
Yeah, if you could put your email into the chat and let me know your team number, okay? In the chat as well, and then I'll be looking for a teammate for you.
Sound good? Okay, let's keep moving then.
Okay, Professor. So
well, I think we should probably take this one offline. So I think you should follow up by email with Dr. Tolman, okay? And we'll try to find a third teammate. And if we can't find one, and you can go forward as a team of two. So you can also say in that email, what do you want? Okay. Okay. So Milestone 1 has been released. You're going to complete it in a team, as I just said. It's due in a little more than 2 weeks, by Friday, February 12th at 7 p.m. It's worth 10% of your final mark. 7% of it is automatically graded. So most of the test cases, or many of the test cases, are public, meaning when you run ECE 297 exercise, you'll see exactly how you're doing on them. There are some other test cases that are private that will run after you submit. They're not any harder, but make sure that you read the specification, which I'm going to go over today, carefully, because there can be some corner cases that the specification talks about that we might not have in the public tests. So make sure that you handle them in case there are private tests that test them. We test not only functionality, we also test runtime. So you'll be told whether you pass or fail certain speed tests. We'll always run your program on an unloaded machine, so there won't be anybody else running. You'll get the fastest UG machine response time you can get. If there are lots of people on your machine, sometimes things slow down. You won't be tested under those circumstances. 3% of your mark will be assigned by your TA based on how you manage the project, how clear your status is and your division of tasks are on your wiki, your coding style, so what does the code look like, use of Git, so did you collaborate well, did you commit and push often with good log messages, and do you know your code. They're going to ask you some questions about how'd you do this, why'd you do it this way, and so on, to see that everybody on the team contributed. So one of the things I just mentioned is this project management, and part of that is what we can see on your wiki in terms of how you divided up tasks and tracked things. So those aren't set up yet. They will be set up soon. You'll get login info, and you can go into the wiki. Only your team and instructors can see it, so nobody else in the course can see your wiki. I'll discuss what should you put on there, what do we consider good status reporting and good project management in tomorrow's lecture, and we'll keep talking about that for another lecture or so after that. The syllabus also has some guidance if you want to start working on this early.
Vaughn, did you want to turn your camera on?
Oh, sorry. Thank you. Did not realize that my camera wasn't on. Thanks, Ken. Can you see me now? Okay, so
yes.
Ken, can you see me? So now I'm going to talk about some background information that you're going to need to complete Milestone 1. So Milestone 1 is you're starting to build the main application of this course, which is a geographic information system, meaning it's to visualize and work with geographic data, city maps. Where we get that data from is an open source database of the world called OpenStreetMap. So I'm going to talk a little bit about that so you know where the data comes from. And I'm going to talk about graphs, which is a more complex data structure that is how we're organizing the data. I know you haven't been taught graphs, so you don't really need to know a lot about graphs because we're going to teach you what you need to know as you go through this, but that's the underlying representation of how is this data organized. So it's a bit useful to understand. Okay, so OpenStreetMap, as I mentioned, is an open source geographic database of the world. It's contributed by regular people all around the world just entering data. The following building is at this latitude and longitude, and it has this stuff in it, and here's where all the corners are, and all sorts of data, how tall the building is, etc. So there's a ton of data there, and people have built a lot of really interesting applications off of it. So what does this OSM data look like? So this is the raw data, which you don't have to work directly with. So I'm going to tell you, you can choose in later parts of the project to work directly with some of this low-level data, but you don't ever have to work with this low-level data if you don't want to. We built an API on top of it that's a bit easier to use. But let me start at the bottom and just explain where's the data coming from. Okay, so OpenStreetMap data fundamentally are latitude and longitude points. So the geography is stored as latitude and longitude. And each point in this huge database is called an OSM node. So that just means it's a latitude, longitude point. And every one of them has a unique integer ID. It's a big integer, 64 bits, which represents some enormous number of, that's an incredible range of numbers. So actually every single node or position that's been entered anywhere in the world has its own unique 64-bit integer called an OSM ID. Okay, then there are data structures in the OSM data that group these points. So a list of points is called an OSM way, and that might form a piece of a road, it might form a piece of a shoreline, it might form the boundary of a park, all sorts of different things. And then there are optional tags on these points and ways, which are key value pairs. So for example, the key might be name and the value might be young. So that might be put on a way, a list of points that represents part of Yonge Street. Another one could be, the key could be natural, indicating it's a natural feature, and the value might be water. So it might indicate this is part of a pond or a lake. There's lots of documentation on this. And Wiki, what you're going to use to document your project, is used by all sorts of projects. So there's actually another Wiki page that's maintained by the OpenStreetMap organization and describes all of this data. Okay, so this data is pretty big. So you can download the data for the whole planet in XML format. XML is very similar to HTML. So if you know HTML, you pretty much know XML as well. But it's big, okay? So for the whole planet, if you download this file, it's more than a terabyte. And it's kind of hard to work with. So what we've done is we've extracted and downloaded several cities. So cities not as big as the whole Earth, so it's a bit more manageable. I see somebody saying they could store a terabyte. I mean, if you want to grab the whole thing and visualize the whole Earth, it'd be above and beyond. So you can go for it. But we decided not to try it. Tim Trent might get pretty mad at us. So we've extracted and downloaded several cities. For example, there's one called Toronto, Canada, .osm.xml. So this is a big file. It's human readable. You can actually find it in the public directories for this course. So if you go to the path that's listed, /CAD2 ECU297 public, you can actually go look at this file. And it's big. For Toronto, it's not as big as the whole world, but it's still a gigabyte. And it looks like this. Basically saying things, well, I don't want to go through the whole thing because you never have to read this. But for example, this says there's a highway, and here's some information about the highway. Okay, so we've downloaded that. The positive about this data is that it's powerful. OpenStreetMap basically lets people around the world enter pretty much anything they want. So there aren't a ton of restrictions on what they can enter. And this XML is text, so you can read it. I just showed you that the file format might not be the easiest read, but it is readable by a human. But the negatives are this data is pretty low level. It can be kind of hard to interpret. It can be a bit inconsistent, so there aren't that many rules on exactly how people names things and tag things. It's entered by volunteers, so they don't always follow the same conventions around the world. It's big, it's a gigabyte for Toronto, and that means it's slow to load. So when we parse and load that file into data structures in memory, it takes us about 45 seconds for code we wrote. So that's kind of slow. It's going to give a slow startup to your program. So it's a bit annoying. Okay, so what have we done? So this is stuff we've done for you, so it's kind of just background. We wrote a program called OSM to bin. This is a standard technique that files that are readable by humans, so they're text files like XML, they're nice in that people can just read them. But they're larger and slower to parse for programs. So we wrote a program called OSM to bin, which reads in that OSM data. It applies a bunch of consistency checks, it organizes it, so it kind of moves the data to a bit of a higher level representation, which is mostly what I'm going to talk about today. That's a bit easier to work with. And then it writes the data back out, only the data it needs. So some data that we don't need, we just don't write out. So that's one way to reduce the size of the file. Another thing we do is we don't write it out in a human readable form. We write it out in binary, and we write it out in a format that is exactly the right format to load up a bunch of classes. It's like perfectly organized. And this makes it much smaller. So we have a file called TorontoStreets.bin, which is the binary form of this Toronto data that we need. And it's much smaller. It's about 1/10 the size of the human readable form. And we can read it in a lot faster. We can actually read this in about a second. And you're going to have to call a function to load this data into memory before your mapping program can do anything. So this means that your program can start up faster because this load function is faster. This technique that I just described, read in a file that's human readable and write it back out in the exact binary form that is necessary to load a bunch of classes, is called class serialization. And there are libraries that can help you do it. We use one called Boost Serialization. This is a standard technique. It's kind of beyond what we're going to teach you in this course, but it's useful to know this exists. There are libraries that allow you, once you have all your data organized in memory and classes, that allow you to just basically write it back out to disk in a binary format that perfectly matches your classes, which makes it much faster to load in. And that's what we're doing in this course. Okay? Okay, so that was kind of background because, as I said, you don't have to deal directly with this OSM data. Now let's get into what you do have to do. So in Milestone 1, you have to implement an API, an application programming interface. So you're writing utility functions. None of these functions is terribly interesting by itself, but they're going to be things you build on in the later milestones. And the act of creating them is also going to help you understand how to work with the application programming interfaces that we give you. Okay, so you're going to build an application programming interface that we call libstreetmap. Well, it's in a folder called libstreetmap in your project. And basically the specification of what this API is, so all the functions in it, is in a file that we give you that you cannot change, okay, because this is a specification, called m1.h. So it's just a header file. It's heavily commented. It basically has about 12 functions in it. You have to implement those 12 functions, and the comments say what those 12 functions have to do. We also, when you set up the project, you're gonna type EC297 init 1, and that's gonna set up your Milestone 1 project. You'll find that you have a skeleton file, so a file with a little bit of code in it, but not much, called m1.cpp. And that's where you can write the definitions of these functions. So the header file just says, how do I call the functions? And it has comments to say what it should do, but it doesn't actually implement the functions. So you've got to do that. You can write them all in m1.cpp if you want, but you can add files, okay? So you can make as many files as you want, organize your files any way you want. You can delete m1.cpp if you don't like it. Doesn't matter. So many people write everything in m1.cpp, but you don't have to. Okay, so that's what you have to write. How are you going to write these functions? These are functions that are going to answer questions about any city in the world. How many streets does it have? Where are the streets? That kind of thing. So how are you going to write those functions? Well, you're going to do it by calling a lower level API. So an API that's not quite as powerful, it's closer to the data that we wrote. So that API is called the StreetsDatabaseAPI. And what it can do is defined by this header file. And again, we give you that header file. You can't change it because you can't change what our functions do. This is what they can do. You can call those functions. So how does that API work? Well, basically what we've done is we took that toronto.osm data. So that's the data that we got from that big open source database. We offline, some weeks ago, we ran a program we wrote called OSM to bin, which took that data and translated it from a human readable ASCII form to a more efficient binary form that exactly matches the classes that are needed in our Streets Database API. So we've already done that. Streets Database API, basically there's one function in it that loads the API. That load function calls into, well, it basically blasts all the data from this big binary file into memory, and now the API is alive and you can ask it questions. And you're going to use this API a lot. Okay, so it's heavily commented. You should actually read through the comments and understand how it works. And in this milestone, you're going to become more familiar with how it works because that's what this milestone is really about, learning how to call that API and organize your code around it. So you're going to use this API to complete milestone 1, and you'll keep using it for later milestones. So it's worth spending some time to understand it. I'll just briefly mention this. There is another API we've written. Okay, so let me erase some of this. There's another API we've written called OSM Database API. This API is basically giving you all the data of what's in this open source database. So we haven't simplified the data in this case. We've just written the code that allows, instead of you having to parse it out of a file, we've already parsed it out of the file, we put it in a binary format, and we can load it quickly into memory. You don't ever have to use this API if you don't want to. For this year, because things are a bit more challenging to do remotely, we've made the use of this API optional. So you can use it if you wish, but it is not mandatory in any milestone in the course. So that might be all you need to know. You might say that's good. I'm not going to learn any more about it. If you want to, so you definitely will not use it in milestone 1 because we didn't write anything that would need it. In milestone 2, where you're visualizing the city, showing information about it, there is some extra information in this lower level API. So you can make your map look better, have additional features if you use it. But again, it's completely optional. You don't have to do it. So I see people saying, can you get a good mark without it? Yes, you can get a good mark without ever using this. Using it or not using it, well, you cannot use it for milestone 1. It would not affect your grade at all because it will have no impact on your functionality. For milestone 2, it's one of many ways that you can make your map kind of do something above and beyond our basic spec. And we do ask you to do something above and beyond our basic spec, but there's lots of different things you could choose to do. You might use some of this data, you might not. So yes, you can get a good grade without ever using this. Okay? And I don't think I can answer the questions about good grade. Like basically, you could get an A+ without ever using this API if you did other things that were interesting. Okay? Okay, so that's kind of the big picture. Now let's talk about how we've organized this map data. I see someone saying, where are these API.h files kept? So if you open your NetBeans project for milestone 1, you'll see that they're in your NetBeans project. NetBeans just essentially points at them. It won't let you edit them because they're read-only, but you can see them through NetBeans. The directory they're in is, I think, /cad2 /ECE297 /public I think it's include or milestone 1. So it's right around there if you're following along on the UG machine, as I see at least one person is. Okay, so that's the big picture. How do we organize this map data? And this is basically, what are these lower level APIs that you're going to talk to? Let me just pop pop up on the stack a little bit to talk about what are you doing in this course from a software perspective. So you're doing 4 milestones. Milestone 1 is building this more full-featured API. So you're going to use the one we gave you, StreetsDatabaseAPI, to implement a bunch of functions that we've specified in m1.h. So this is a little piece of m1.h. Okay, so that's copied straight out of m1.h. And it basically says you need to write a function that is called findstreetNamesofIntersection. Given the ID of an intersection, you have to return a vector of strings that are basically the names of all the streets that meet at that intersection. So maybe it's Young and Bloor. That might be the return. And the comment says, what is it? Which basically is what I just told you. Some of these functions will be performance tested. So when they're performance tested, we also put a speed requirement on each one of them. So this one is intended to be fast. So the performance test, is going to check that, and you're going to have to code this to be it doesn't have to be the world's best implementation, but it has to be a pretty fast implementation. We don't interpret high as like this is the fastest code we've ever seen, but it means you've used good coding techniques, appropriate data structures to get a pretty fast implementation. Okay, and the tests that we've released, EC297 exercise, if there's a speed requirement, EC297 exercise tests it. So the header file tells you, you should try to make this fast. Exactly how fast, the EC297 exercise tells you, because it'll tell you exactly how long it took, how long you had, and did you pass or fail. Okay, so how are we going to represent a street map? Because that's what you're trying to do in this project. And you haven't been taught this in 244. So often 244 teaches this, but this year no. But that's okay, because you don't need to know much about graphs. But who has heard of a graph? So I know you weren't taught it in 244, but if you have or haven't heard about it, just want you to type that into the chat. Okay, so it seems like a fair number of people have heard about it. Some have not, but a lot of people have. Okay, so it seems pretty split. As I said, you don't need to know much about it. We'll teach you what you need to know about graphs. So a graph is a very general data. It's beyond kind of a data structure. It's kind of a data idea, a way of organizing data. So it represents connectivity between items. So it consists of 2 components. It consists of vertices or nodes. Those are synonyms. They mean the same thing. And those are commonly they're commonly referred to by the variable v. And it also has edges between connected vertices. And those are commonly given the variable name e. So sometimes you'll see in textbooks things like my graph is equal to the vertices and the edges. That's all that means. So it represents connectivity. What are the things? Those are the vertices or the nodes. And then which ones are connected, which is the edges between them. Okay, so you've already used special cases of this. A linked list is a form of a graph. Okay, so a linked list looks like this. You've got nodes that are where you're storing resistors or some other data, anything you want, and there are edges between them. So those are your next and previous pointers. Those are edges. They represent connectivity. Okay, but in a linked list, every node has at most 2 edges, because it might have a next, it might have a previous, it never has anything more than that. A binary search tree is also a form of graph. Okay, so a binary search tree, the nodes again could be anything. In the second tutorial, we used the example of a node could be a domain name and its IP address. And then the edges represent children. So in a binary search tree, you can have a left child and a right child. And sometimes you might have, one child but not the other, or you might not have any children. So in a binary search tree, each node connects only to its children. You have at most 2 edges per node. This again is a graph. We have nodes, we have edges between them, and it satisfies a bunch of restrictions. A binary search tree is a special form of a graph that matches, these restrictions. Just like a linked list is again a special case of a graph. Okay. I'm just looking at this place. Okay, so I'm seeing if anybody else is asking questions in the chat, but it looks like that's not a question. Okay, so those are special cases of a graph. In general, a graph can have any number of edges at a node, so it can have arbitrary connectivity. And we're going to represent these street maps as graphs, but they are much more arbitrary. You can build cities with very different street structures, so they're not going to be as restricted as a linked list or a binary search tree, but they're the general form of this data structure that you've already been using special cases of. Okay, if you want to know more about graphs, this is a classic book about data structures and algorithms. So if you want to know about hash tables, this which we already talked about in the tutorial, you go look in this book and it'll tell you all about hash tables. If you want to know about graphs, it's in chapter 22 of this book, and it has many algorithms are actually written to work on graphs or described as working on graphs. So you'll find there are a whole bunch of different algorithms in here that work on graphs too. So chapter 22 is really about just what is a graph. You don't have to read that. That's just basically if you're curious and you want to know more. Okay, so how would you represent a street map? So we're going to represent it as a graph. So graph, which has vertices and edges. So it looks like this, right? Here's my graph. It's got vertices, which are the circles, and it's got edges, which are lines. Those indicate that some of these vertices are connected. You know, these two vertices are connected, but this vertex and this vertex are not connected. So that's what this graph is indicating. If I want to represent a street map, so I'm showing up here a little piece of downtown Toronto, what should my vertices be? What should my edges be? Whenever you're going to use a graph, you have to decide, well, those two questions. What are my vertices? What are my edges? You can represent a lot of different things, so we need to make that choice. Okay, so I see some people saying, so Isidore and Taha are saying intersections. Intersections are vertices, and the streets are edges. Okay, so and I see generally agreement that the vertices are going to be intersections. And that makes sense, okay? They're kind of points in space. And it makes sense that I could say which intersections are connected together. And then I see some questions. The edges seem a little trickier. So I see people saying, well, maybe the edges are streets, but what if the streets are curved? That's a little trickier. Yeah, so the edges are a little more tricky, but people have the right idea when they're saying the edges are streets. We're not going to make the edges entire streets. You think about Bloor Street. Bloor Street is really long, and it actually goes through a lot of intersections. So street's not quite, it's the right idea, but it's not quite the right thing to represent the edge. We have several vertices on a curved street. You could have several vertices in a curved street. So yeah, that'd be a valid way to do it. I see some people saying street segments. Yeah, so what we've chosen, and there are multiple ways you could do this, but we've made a choice of how to do it, which we think is pretty logical, makes working with this easier. And sometimes you can make choices of how you represent things that make life a lot easier. So the vertices are intersections, and the edges are street segments. A street segment is basically a piece of a street that goes between two intersections. So it's essentially a city block. It's not easy to use an entire street. I can't say it's impossible because there's lots of ways to organize things. But if we use the whole street, Bloor Street goes through a ton of different intersections. So it's not really an edge. But a street segment goes just between two intersections. It's like a city block length of a street. Okay? Is a dead end a vertex? Yeah, and there can be special cases here. Like I could have things like this, like a vertex where you can have a street segment that goes to it and it doesn't go anywhere else. Okay, so this is like the end of some alleyway, and there will be a vertex for that. It's an intersection with only one thing going in. You will find that in the data. Can a vertex have 0 edges attached to it? I don't think we have any intersections with 0 edges. I don't think that ever happens. Okay, so yeah, this is how we represent it. Intersections are the vertices, and street segments are the edges. And I see people asking, for more detailed maps, would each establishment along a street be a vertex? Yeah, and you could do that. So you could decide, I want to make an even more detailed map. I want to make my vertices, maybe every business, because I really care about businesses. So this isn't the only choice we can make, but because what we care about is kind of how to get from one point to another, we've decided that we'll represent it as a graph of intersections and street segments. But people are right, that's not the only way to do it. I see people asking, what about a roundabout? So that's actually an interesting question. You will find roundabouts in some of these. One of the city maps we give you is London, which is full of roundabouts. A roundabout generally we modeled as a bunch of intersections. So there's streets coming in, and there are curved street segments coming in and curved street segments going between the roundabout. And people are leaving at certain spots. So you can represent a roundabout using a graph like this as well. And I saw some people saying, well, what if the street segment is curved? And I'm going to show you that we can represent that as well. Okay. These are all really good questions. So how do we identify each vertex? And some of these questions, hopefully, as we go through this, will become more clear. So I'll keep going, but I keep asking if I don't answer your questions. So lots of ways we could identify a vertex. The way that we choose is one that helps you make efficient data structures. So every vertex, which is an intersection, it has its own unique integer ID. And these integer IDs, we've chosen them to be small and contiguous. They go from 0 to some number. So for Toronto, we have an API call in StreetsDatabaseAPI called getNumIntersections. Okay, so you basically say, I want to load Toronto. That's the first thing you do. Before you load a city, you can't ask any questions. You can't say, what's the number of intersections when you haven't even loaded a city? So you load a city, you say, give me the number of intersections. And for Toronto, the number of intersections is about 166,000. All of the intersections in the map of Toronto will be numbered between 0 and that getNumIntersections value -1. Okay, so if this is my tiny city that only had 5 intersections, they'd be numbered from 0 to 4. And you're going to see this actually gives you some nice choices of how you might want to store data associated with those intersections. Basically, it makes it not easy to store data in vectors because the numbers that we're using here start at 0 and go up to some number -1. That kind of perfectly matches how a vector works. And a vector is a very efficient data structure, so this kind of helps you write fast code. Okay, there's also a name. So every one of these intersections has a name. That's really intended just for user output. So the names might be things like Bloor and Young, Bay and College, etc. But they're not guaranteed to be unique, whereas these integer IDs are guaranteed to be unique. They'll always identify only one intersection. So you want to really write your code to work with the integers, which also is faster than working with strings. And these strings you should only interpret as something that's useful for printouts and so on. Okay, what about street segments? So street segments are the edges. We use the same exact ID. We give every single street segment, so city block length piece of a street, a unique integer ID. It again starts at 0 and it goes to some number, which is different for every map. So for Toronto, if you call one of our functions getNum street segments minus street segments, it'll say there are about 215,000 street segments in Toronto, and they're all numbered from 0 to 215,000 -1. Okay, so what I've drawn in blue here is that basically all of these edges, this edge is a street segment and it's got ID 1. So they've all got different IDs. They don't have names. So we don't put names on the street segment because generally nobody names a city block. One thing to watch for in your code is that these IDs for intersections and street segments overlap. So they're both small integers. So, does ID 0 refer to this vertex, or does it refer to this edge? Well, it could be either. Those both have ID 0. So you have to remember in your code, well, what API did I call? What kind of data did I just get back? Did I get back a street segment ID, or did I get back an intersection ID? So you got to keep track of that in your code. You should name your variables carefully. Don't call your variables I, J, K. Call them intersection 1, street segment A, that kind of thing, it's going to be a lot easier to keep track of what variable is storing what. Okay, so we're using integer IDs for everything. And as I said, you could get, if you're not careful with your variable naming, you could get confused, so try to be careful. To help you, the StreetsDatabaseAPI that you're going to call uses typedefs to help make it a bit more clear. Who's familiar with typedefs? Did you ever study typedefs in 244? Okay, okay, yeah, looks like you did. Okay, so that's good. So typedef is pretty simple. It's basically like just defining a synonym. So this line, typedef int StreetSegmentIndex really means this new name, StreetSegmentIndex, means int, okay? And this other line says this other name, IntersectionIdx, also means int, okay? So in our code, we could just write int all over the place, but we've defined these synonyms for int to try to make the API more self-documenting. And then you'll see in our API, we have functions like this, get intersection name. Get intersection name takes an input argument of intersection index, which really is just an int, okay? So that's just an int. But by using this name, we're telling you the int that you pass in should correspond to the ID of an intersection. Don't pass me some random integer because bad things, something's going to happen that's bad, right? It'll be out of range, our API is going to crash. And it returns a string. What's the name of that intersection? Okay, in your code, you can do things like this. It'll compile, it won't give you any warnings, it'll be fine. So you can say int my index, but this isn't very clear. What kind of index is this? If in your code you instead write intersection index, my intersection index, it's pretty obvious to you, your teammates, your TA, okay, that's the ID or the index of an intersection. So much better to use names like this. You'll do better for in your coding style, it'll be easier. Does C++ allow casting from one typedef to another? A typedef is really just a synonym. Okay, so typedefs really don't imply casting or anything. It just means, this literally means whenever I write intersection index, the compiler knows you really mean int. So there's no casting involved or anything. You could still have casting after that if you tried to convert like a double to an int or a double to an intersection index. It doesn't really make a whole lot of sense. But if there's some automatic casting from double to int, yeah, the compiler will still do it. But this is really just, think of it as synonym, okay? And I don't know of a way to get C++ to give you a warning, unfortunately. So these, if you just assign an intersection index to an integer, the compiler is going to be perfectly happy with it. So this is really about just trying to make your code more self-documenting. Anyway, those are questions in the chat if you're wondering why am I saying those things. So it's good probably to follow along in the chat as we're going through this lecture. Okay, what kind of graph should we use? There are two basic kinds of graphs. There's undirected and directed. Okay, so undirected means an edge indicates, this edge, for example, indicates that this node and this node are connected. And there's no sense of direction. They're just connected. You can go from A to B, and you can go from B to A. There's another kind of graph called a directed graph where all of the edges have direction. So in this graph, if I label these again, if I label that A and B, I can go from A to B because there's an edge in that direction, but I can't go the other way. So what kind of, just type this in the chat if you think you know what kind should we use, undirected or directed. Okay, so I see lots of people saying directed, they're one-way streets, and that's exactly right. So we have to use a directed graph. If you used an undirected graph and Milestone 3, you're going to be giving travel directions, you're going to produce a lot of very dangerous travelers who basically pay no attention to one-way streets. It's not even something they can conceive of. Your program has no notion of it. So you're going to use a directed graph. Okay, how do we represent two-way streets? So two-way streets, basically you can represent as two edges. So if I can go both ways between, let's say this was C and B, then I put two edges in, one way, one the other way, and that's fine. Okay, so how do we represent this in the API we've given you? This Streets, sorry, I actually got the wrong name up here. It's the StreetsDatabaseAPI. We represent it with a graph that basically looks like this. Okay, you can't see the graph, but when you're calling our API, this is what you're talking to. We have edges between the various nodes, and those edges essentially have a property that have properties that tell us, are you an edge that only goes this way? Are you an edge that only goes the other way? Or are you an edge that goes both ways? Okay, so the queries we've given you let you check, is there an edge? And then if there is, does it go both directions or one way or the other? So those queries, to essentially extract the graph from our API, you can ask, how many street segments connect to me? So I'm an intersection, say the one I've just circled. How many street segments are there? So I'm an intersection where 3 pieces of street come together. Okay, so I'm kind of an unusual intersection. I'm like that, maybe. I can ask, tell me more. Tell me the IDs of each of those street segments. So maybe this is ID 10, maybe this is ID 12, and maybe this is ID 2000. So I can get those 3 IDs. And then from those IDs, I can say, okay, street segment 2000, I want to know more information about you. So I can ask for something called street segment info, a data structure that's going to give me information about, if I asked on 2000, I'll be told information about that particular edge. And it's all in the header files. But the key information from a graph perspective is there's a from. Okay, so let me erase some of this. Let's say I'm doing 2000, this edge. So there'd be a from intersection, which might be that. A to intersection, which might be that. These both have IDs. So maybe this is ID 1000. Maybe this is ID 3000. Whoops. And there's a bool one way. Okay, and in this case, it is a one-way street. So this bool would be true. Okay, so that would describe this. Let's see if I can get a different color here. This street segment is what I've just described. When this bool one way is set to true, you always go from the from intersection to the to intersection. If this Boolean one way is false, then you still ask for the from and to, but they don't really have any meaning, right? So for this edge up here, this intersection might be from, and this intersection might be to, but because the one way is set to false, that doesn't really mean anything. You can go both ways anyway. So hopefully that makes sense. If not, type in the chat. So what I just described is essentially how you get the connectivity. You extract the graph, and that's really important. That's important, very helpful for drawing things, but it's also helpful for pathfinding, which you're going to do in Milestone 3, where you try to find travel routes from one spot to another. We don't just give you connectivity, though, and this is common when you're describing things as a graph. You often have extra data that goes along. It's more than just how many nodes are they and how do they connect with edges. You often have additional information that helps you visualize or interpret this graph. And we have that extra information as well. So intersections, I already told you they all have an ID, but beyond that, they have an ID, and using some of the API calls, we can figure out what edges they're connected to. And they have an ID, they have a name, and they have a latitude and a longitude. So we know where every one of these intersections is. The street segments, I already talked about the fact that they have an ID, and they have a one-way. They have a speed limit as well, so you can tell how fast you're allowed to drive along that street segment, and that's going to be important when you do pathfinding. And they have something called curve points. So this goes back to a question that people asked, some people asked at the start. What about curved streets? What about roundabouts? Where the path between 2 intersections might not be straight. So we encode that as curve points, and the curve points basically tell us what is the shape of the street. If it's street segment, if it's not straight. And there's another index called the street index. So the street index is another integer ID that allows you to look up information about, maybe I'm part of Yonge Street. Okay, so I'm a street segment. I'm not all of Yonge Street, but I'm part of Yonge Street. This street index will tell me, okay, go look at street number 33, and that's going to tell you more information about what street you're part of. Okay, so let's talk about those curve points. If a street segment, so the street segment can answer the question, how many curve points do you have? So if it has 0 curve points, then it's just straight. Okay, it has a from and a to intersection, and it's a straight line in between those two things. So that's pretty simple. But a lot of city blocks are not straight. If they're not straight, then they'll have more than 0 curve points. This particular example has 2. And that just defines the path between the intersections. And it's an ordered path. So I basically start here, and I go through each of the curve points in sequence. And that each of the curve points has a latitude and a longitude. This defines the exact shape of the street segment. And you're going to find that, for curved streets, we would represent it more precisely than this. So I'm showing you two curve points, but if this was actually a smooth curve, then it might have 10 or 12 curve points, so that it looks pretty smooth. Okay, streets. So I mentioned that a street segment can tell you that it belongs to a certain street. So let's take Young Street. Young Street is really a group of street segments. So we've got actually all these little pieces of city block length street. So those are 4 street segments that I'm showing here in blue. A street is also given a unique index, and it's again an integer, but you need to keep straight that this is now the index of a street, not anything else. You can ask the API how many streets are there, and all these indices will be between 0 and num streets -1. In Toronto, there's something like 30,000 streets, so not as many as there are intersections or street segments. It'll have a name. This is the name that you would be used to using, like Young Street or Bloor Street. That name may not be unique. So in a big city, you might have a whole bunch of different main streets. So you shouldn't assume that this name uniquely identifies a street. This integer uniquely identifies a street. I mean, integers are faster to work with, so it's better, and also we guarantee it's unique. Whereas the name, we can't guarantee that. Okay, so those are streets. We also have something called points of interest. Points of interest are not really connected into the graph. They're just other information that we've put in the geography. Each of them has, again, a unique index, so an ID, an integer ID. It has a location, so that's a lat-long location. So you know latitude and longitude, so you know where it is. There's no connectivity information. We don't tell you it's connected to this intersection or anything like that. So it kind of just, it's a business, it's exactly here. And it has a name, which is generally not unique, like it might be Tim Hortons. And there will be a lot of points of interest that match the name Tim Hortons. So every one of them will have a different index, they'll have a different location because they're not going to be on top of each other, but many of them might have the name Tim Hortons. Okay, and I'm almost done with this. I'm just going to see if I can finish the last couple things here. Okay, another thing that's in this libstreet database are features. Okay, so what are features? They're the outlines of interesting things that are not streets or intersections in cities. So you can ask this libstreet's database API, tell me how many features there are, and then tell me information about each one of them. Each of them has a feature type. So the feature type can be things like lake, building, park, stream. So what are you? What kind of thing are you? And we've divided things into all these features into about 10 categories. And then each of them has a set of latitude and longitude points. And those latitude and longitude points, if the first location is equal to the last location, then it defines a polygon. So for example, it could be, if it was of type lake, then its first point is equal to its last point, then it's a closed polygon, it's a lake, I'll probably draw it in blue. If the feature is a whole bunch of latitude and longitude points and the first one's not equal to the last one, then it's a polyline, meaning it's just a sequence of line segments. So that might, for example, define this little trail. It's not a road, so we didn't make it a street segment, but it's something that you might draw, which is maybe a trail or a shoreline. Last thing, which you don't need to use in this course at all, but you might choose to use in Milestone 2, is the OSM ID. If you remember way back to the start of the lecture, I said that in the low-level OpenStreetMap data that we're processing for you, every single latitude and longitude point that they've put in the whole database is given a unique integer ID. And it's got to be a big integer, 64 bits, which can store a huge amount of data. And that ID is globally unique. It will be different for every single point that's ever been entered for anywhere in the world. So yeah, it's a huge number. The range goes from 0 to about 10 to the 19th. And optionally, in future milestones, if you want, you can use that to look up more raw OSM data from the lower level API that we wrote, which is called OSM Database API. You will not use that in Milestone 1. Some of you might choose to use it in Milestone 2, which is why I mentioned that. And that's pretty much it for this lecture. I just sort of end off here of, okay, we'll talk about this some more, the lecture tomorrow. But basically, you get started in this by reading the handout, reading m1.h, where we basically giving you the specification. What do you have to write? And the comments say, what does each function have to do? This is good practice. Your header files should define what a function does. If you have comments about how something works, you put that in the CPP file. So all these comments are, what does it have to do? EC297 exercise has detailed unit tests. We'll talk in a couple lectures about what are unit tests, but basically your really detailed specification is in EC297 exercise. You have to pass, to get full marks, you have to pass all those tests. So you may not pass them all, you'll get part marks, that's fine. This is called test-driven development. The tests are checking your code, and the tests are actually, we've completed the tests before you've written your code. That's actually a good practice, test-driven development, where these tests are the detailed specification. And as I mentioned, many of them test functionality, some test speed, and we also run val grind to make sure that you're not doing bad things to memory. And that also helps you debug your program. So so the question, are unit tests provided for you? Yes. So EC297 exercise runs a whole bunch of unit tests that we wrote that are what are called the public unit tests. And you can also go look at their source code and so on if you need to debug them. We talk about how to do that in the unit test quick start on Quarkus. We also have some unit tests that we are similar, but we haven't released, that will run after you submit to make sure that you've also thought about corner cases and read the spec. You haven't solely used EC297 exercise. But the tests in EC297 exercise are pretty complete, so they're going to provide a pretty complete, but perhaps not perfect test of the specification. Okay. And with that, I'm gonna end the lecture. So I went a few minutes over time, but this is kind of a natural place to end, so you can get going on this milestone. And I'll stay on the line in case there are questions.
Hello.
Hi.
Sorry, I had a quick question. So earlier when you said two-way streets are two edges, right?
Yeah.
So what would be the point of having the one-way Boolean then?
Well, okay, so that's a good question. Let me go back and show you. The normal way you would store two-way streets is with two edges in a what's called a directed graph. Okay, so let me erase some of this. Yeah, so we need to make sure that our graph has direction to represent two-way and one-way streets. And what I'm showing you on the right-hand side here is a conventional way to store that. You store two different edges if it's two-way and one edge if it's one-way. The API we've given you, we found it a little more efficient to store it in a slightly different way, which is basically we store, does the edge exist? That's the first thing. And then we store properties on it saying, does it go both ways? Does it go one way? And if it goes one way, it will always go from the from intersection to the to intersection. So we gave the edge, instead of just saying it has two intersections connected to it, we gave each of them, essentially said which one is the from and which one is the to. So that's the way our API works, because this actually let us represent the graph a little more efficiently. We actually have quite a bit of data on each of these edges, all the curve points and so on.
Yeah.
So because of that, it's more efficient for us to actually store the edge once, because it comes with a lot of extra data, and then essentially put properties on it to say, is this representing a single edge going one way, or is it really representing two edges going both ways, but they share all this other data? So you don't have to worry about the details of exactly how we stored it, but that's what we did. And our API reflects that. When you ask the queries, you essentially ask, tell me the street segments that connect to this intersection, which is get me the edges. And then you can look at those street segments and see, are you one way or not? Does that make sense?
Yep, thank you.
Let's see. Will our streets be given additional constraints such as traffic load for any particular segment? No, we're not going to give you traffic load. Yeah, so that won't be a required thing. In past years, sometimes there are students who, in Milestone 2, for example, we say it'd be good for you to add, you should add some features that we haven't asked for, but you can decide what they are. Some students have written what is a relatively challenging feature where they actually go out to the web and they get traffic data and they'll actually draw that on top of their street map or allow you to query it somehow. So you can do things like that, but we don't require it. Let's see, I see a question. How long should this take if you sit down as a group during the weekend, and how hours should we budget? That's a really hard question. So, and actually other profs ask me this too. So not all your time, because I think I'm on speed email from the 231 profs that people spend too long on 297. So should not be anywhere near all your time. This milestone shouldn't take too long. It's difficult for me to give a perfect hours because it depends on how well you split up the work, how fast you debug, etc. With most coding, and this is no exception, you usually spend longer debugging than you do writing the code. So if you're very efficient at debugging, and you're probably not that efficient at debugging right now, but that's one of the things you want to practice. That's actually part of the point of a course like this in software development experience, is you get better at it. So I don't know, it's hard to give an exact number. If you split it up evenly across the 3 members and you debug pretty efficiently, then yeah, it probably takes a few hours each. Maybe 4, I'm not sure. If you, and for the typical group, I think it's going to take longer than that because it's going to take longer to debug it, and there'll be a few thorny issues that you just hit. I don't know what they are. It'll be different for every group. Of like, you've got some nasty bug and it takes you a while to solve it. So, for I think the typical group, it's going to be, maybe it takes a solid day of work for each person. You could do it significantly faster than that. You could do it significantly slower than that. So it's really hard for me to give perfect numbers. And that's actually something that would be useful for me to maybe to poll people with afterwards, is how long did it take? See, am I being naive, or why would this take longer than a few hours? If you actually sit down with your teammates and you kind of divide up the work, there are about 12 or 14 functions. So each of you have to write, 4 to 5 functions. And we're going to talk about how to make them faster. The performance tests mean that you're going to have to create some data. You won't be able to answer every question just by asking our APIs questions without storing anything, or it's going to take too long. But if you divide it up, who does what, and you're efficient at debugging, you're right. It's definitely doable in a few hours. But often things go wrong, and it takes time to learn how to use these data structures. So it also can take significantly longer than that. And don't feel bad about that. You're just kind of learning how to debug faster and how to use STL better.
Can I follow up on that question?
Sure.
So me and my team were looking through the lab handout or the milestone handout, and it's obvious that a lot of the functions are not a lot. There's a decent amount of the functions that depend on each other. Like you can use one function when you're calling another function.
Yeah, it's true.
And I was wondering, how would you recommend dividing that up, since we're obviously collaborating? Because you don't want to group. What I was thinking is divide the work up so that relevant or similar functions, one person's doing them so that they can implement them both at the same time. But then again, the other approach is just to divide it more evenly. And what I'm wondering is, which path would you recommend?
Yeah, it's more efficient to group functions. You're right. Some functions look clearly related and can build on top of each other. Try to assign those to one person, right? Because your most efficient communication is a person who's just discussing things within his or her head. So yeah, I wouldn't randomly assign the functions. You may not be able to do a perfect job either, though. You haven't written them all. So, and I'll talk about this some tomorrow, may not get through it all, so some may slip into Wednesday of next week. How do you attack a project as a team when you're coding? So you do want to sit down and say, okay, who does what? We want you to write that down on your wiki. That's part of the how did you get there? Did you divide the tasks? Did you make a plan? You don't have to stick to the plan at all. We want to see that you have a plan, and it should have deadlines. One of the things that gets people into trouble is perhaps some team member doesn't really feel much deadline pressure and doesn't write his or her functions until the last minute. And now the other teammates are basically going, well, we can't really allow this to happen. We have to write the code for that teammate as well. So you don't want that to happen. So you want to set deadlines that are internal deadlines that are well in advance of the actual submission, because it allows you to react. Maybe somebody's having a ton of trouble debugging this one function, but everybody else is done. They help out. So that's part of what makes it more efficient too, and helps divide the workload. But you're right. You're trying to group related functions. You're trying to roughly balance the workload, which means you think you've given some easy and some hard functions to everybody. You won't get it perfect. So you just take an initial cut at it and you say, okay, well, we're going to work on this for a few days and then we're going to reconvene. And if it turns out that the functions we gave you are harder than we thought, or you're just struggling with them, we can reallocate. That's very hard to do if you went, well, we're going to leave it all to the last 2 days or 3 days. We're going to divide them this way and it's all going to work out. And now it's a really high stress situation, because if you mispredicted how things go, you don't have much time to react. So don't do that. Try to make it come together earlier.
Thank you for the comprehensive answer.
You're welcome. Let's see. How should you plan about attending and submitting a lab session? So we'll post instructions about the lab session. I haven't done it yet, partly because I don't want to confuse people because they're still doing Milestone 0. So Milestone 0 is wrapping up this week, and then you have 2 solid weeks to work on Milestone 1. But obviously you can start right now. That's why we're doing the lectures, and I've released the milestone. And actually, one of these, go to the tutorials if you aren't already, because one of these 12 to 15 functions we're actually doing in the tutorial. So you go to the tutorial, one of them, if you can write down notes as you're watching the tutorial, you can submit that function. Okay, so that is kind of a literacy test. But we've already posted, I think I've posted who is assigned to what TA, unless I just imagined I did that. So if you go to Quarkus, you'll see where it says who is my CI. There's a tab for that. Your TA is also there. That's going to start next week. You will meet with that TA. So as I said, I'll do a Piazza post to give more information. But the basic idea is the TA is going to split up the lab period and have breakout rooms where he or she meets with each team during part of the lab period, and is also available in a Zoom meeting for just general questions during the lab period. Does that make sense? For submission, you can submit anytime you want before 7 p.m. on the 12th. Doesn't have to be in the lab. Your TA will ask you questions. Well, your TA is going to see how you manage the project and give you feedback as you're going through, answer your questions, but your TA is not going to be grading you until after the submission. So it'll be after reading week. Your TA is going to look at your wiki, is going to know how you were working during the lab, is going to look at your code style, etc., ask you questions about how you did things, and it's after reading week that your TA will assign those 3 marks that are the more subjective ones. The ones that are marked automatically by our unit tests will be run on whatever your last submission is before we cut off the submission. We basically, after 7 p.m. on February 12th, you'll basically get a message saying submission has been closed. Your last submission before that is what we'll grade. If multiple team members submit, we keep the last submission from each team member. We will grade them all. We will give the whole team the highest mark. So, if you wish, if you actually have a disagreement with the teammate about, 2 different ways to code something, and each of you code it, you can actually submit both, and we'll grade them both and give everybody the higher mark. Does that make sense? And the question of, is that the TA for the lab? I think you're referring to, that list that's on Quarkus, and that is your TA for the lab once you're in Teams. So not this week, but next week. Do you talk about your milestones with your CI? Yeah, you should talk with about milestones with your CI. I mean, your CI represents, a client or a business manager, not an engineering manager. So your CI is probably not going to have technical advice on, exactly how you should speed up some particular function, but often will have good advice on how can you communicate effectively as a team, divide up tasks. If Bob's not responding to email and nobody can figure out what Bob's doing, can lead a discussion within the team about how can you work together better. If anyone on the call is named Bob, it's a random name. I'm not picking on you. So I see a question. What is the wiki? So wiki is a very easy and fast to edit web page. It actually comes from the Hawaiian word for fast. I think wiki is fast in Hawaiian. If you've ever used Wikipedia, which I'm pretty sure everybody has, Wikipedia is built on top of wiki. It's used heavily in industry, heavily in open source as a way to very rapidly essentially take notes that go into a web page. I will be probably late tonight or tomorrow setting up all the wiki pages. So every team will get information that's mailed to them about here's your wiki page, here's how you log in. And there's lots of documentation on wiki. We point you at some. And it's basically a very easy to create web page where you can write status notes and put tables of who's supposed to do what, anything you want. Okay, so it's intended as a way for you to communicate with your team where the communication is persistent, like you can see what did people do, and your TA can communicate with you using wiki as well. So it's a good way to organize projects. It's much better than writing down notes on a piece of paper or sending emails about who's doing what. I mean, you'll do some of that as well, but this is how, again, one of the common techniques used in industry and in large open source and other projects to collaborate. Everybody can edit it, they can all see it, and it's fast to edit. It's much easier to create than a regular web page. Does that make sense? Okay, so it sounds like it does. And your TA is going to give you feedback about it. Like the idea of this is your TA is going to look at what have you written on your wiki and say, you didn't write much of anything on your wiki, or you wrote a bunch of stuff on your wiki, but it all seems to be kind of irrelevant. I actually want to see who's doing what, and that you guys have set some deadlines and that you're tracking whether or not the deadlines get met. So you're going to get feedback on this. I'll give some guidance in the lecture. There's a little bit of guidance in the syllabus. And you'll be given a lot of formative feedback as you go through this from your TA. And the reason for that is not just to micromanage you, it's basically to teach you best practices in project management. So, and it doesn't have to be wiki, but wiki is a common way to do this. Having written notes accessible to everybody is crucial. That's a good practice. And then having clear ownership of tasks and clear deadlines and clear status of whether they work or not is also crucial. So that's what your TA is going to be looking for. Okay, so thanks everybody. Are there any other questions? Sure. So feel free to unmute yourself.
Yeah. So on the webpage, like you've posted what CI each team has, right?
Mm-hmm.
So we didn't receive any contact from that CI, and we've received some of the contacts from a different CI. So we were confused about who is our CI now.
Okay, so go by what the web page says. I think Maria, if it was Maria, she sent an email with an earlier assignment of teams that we had to revise because we found some problems in it. So if you had an email from Maria, I'm going to mispronounce her name, I think, Chioni, and now you see there's a different CI assigned to you, then it's probably that she sent you an email on the earlier allocation. Is that the right name or not?
Yeah.
So go by what the web page says.
So it's fine if we didn't attend the first meeting with the right CI then?
This week's meeting was really just it's not a big deal. You should send an email to your CI if you haven't. Have you already had your tutorial session for this week?
Yeah. And also we don't know how to contact our CI.
Their email is on the CI info, I think. If you go for Zoom links, click on the Zoom links on the course webpage. It's Zoom and email links. Maybe you have to change the name.
Zoom links, okay. Okay, I see.
Yeah, so email your CI And basically all the CI was doing with teams this week was setting up a meeting time for the future, which might be in your tutorial time slot or it might be something else, but it's something that works for everybody, and giving you some introductory information. So you can sort that out by email too. But you should contact your CI to get that going.
Okay, thank you.
Okay, so see, interesting question. We're getting data from the web for Milestone 2. Do we need to code that functionality in C++? We give you a quick start guide on how to do it in C++. So there's an API called libcurl, libcurl. It's really a C API, but C++ includes all of C. So you can query things off the web from C or C++. If you want to do it in some other language that exists on the UG machines so that you can demo it to your TA, that's also fine. You have to interface that language to C++, and there are ways to do that. You can make system calls and so on. So you basically just decide what is easiest. Or if you, we have had teams in the past who will write something in Python, because Python has some nice libraries and functionalities for querying the web, and they'll get that, and they'll basically call their Python program from their C++ program and grab the data from it. That's fine. You don't have to do that. As I said, we will release a quick start guide during Milestone 2 on this libcurl. So how can you call the web from, we'll query things on web pages from C. But yeah, you could do either. And this is totally optional. So I would say that, it's a relatively advanced extra feature where you're kind of trying to do really well, and I'm going above and beyond to go out and query the web. So it's definitely going to be a minority of people who try to do that. It's not mandatory by any means. We have a quick start guide on it to kind of help you. If you are interested, you can kind of look at, all right, how would I do this from C and how hard does that look? And you can decide whether you want to go for it or not. Any other questions from anyone on the line? Okay, if there are no other questions, I'm going to stop the recording. And thanks, everybody. Have a good night.